Hello guys, welcome to the Python series. In today's video, we're going to look into the fourth module, which is the cmath module. So in Python, cmath module can be used as a different built-in module that allows the user to use mathematical tasks for complex numbers. So the module accepts int, float, complex numbers. It also even accepts Python objects such as underscore, complex underscore, or float underscore underscore methods. So the methods in this module almost always returns a complex number. So if the written value can be expressed as a real number, then the written value for the imaginary part would be 0. If the written value can be expressed as the imaginary number, then the written value for the real part would be 0. Some of the examples are cmath.phase, cmath.polar, cmath.sine method, cmath.log, logarithm base 10. There are also some more methods which we are going to be discussing further when we solve the examples for this module of -4. So when you essentially try it out into a calculator, we get saying a math error, say that this is not possible. So when we try it out in a complex number, when essentially we get root of -4 to be 2i. Here I nothing but signifies square root of -1. So this I is nothing but square root of -1. So that's how you multiply this square root of -1 with the root of 4, which nothing but 2, and 2 into root of -4, 1 is nothing but root of -4, which is this 2i. So when we multiply both of this I with 2 or square root of 4, we just get 2. So what is a complex number? Complex number is signified by z is equal to x plus iy. So here x is the real part and iy both together will give you the imaginary part. So this is what a complex number is denoted by. So let us take an example of a complex number. Suppose let's take 5 plus 2y, and we find out the modulus. Modulus of z is denoted by root of x square plus y square. So here in this case, for example, it will be 5 square plus 2 square. We get it to be root of 29. So when we find out root of 29, it's nothing but 5.835. So this is modulus of z. So when we want to find out z, it can also be written as r in polar form. R is, yeah, polar form is denoted by r comma theta. Z is in the form of r or theta. Now how do we find theta or the argument? Theta is nothing but tan inverse of y by x, which will give you the argument or the phase angle theta. So now let us understand how do you convert a Cartesian coordinate, Cartesian form into a polar form in a complex number. So in a complex number, z x comma y is denoted as the Cartesian form, and we convert this into the form of polar form, which is r and theta. So first, let's take a graph. Sorry, that was a very bad one, bad line. So let's take a new one. Let's say this is our graph, and let's denote a point over there, which is 3 comma 4 in the Cartesian form. 3 comma 4 and x 3 in the x-axis and 4 in the y-axis. So let's join this point from the origin 0 comma 0, and let's join this to this point and connect it down, and let's take this triangle angle to be theta, and this is y and this is x. So we connected from the origin to this point. So next, let's see how we convert this Cartesian form, which is in the form of x plus iy, into uh, the polar form, which is in the form of r cos theta plus I sin theta. So cos theta is nothing but, when you look at this, you can see that theta, here theta is nothing but cos theta is adjacent by hypotenuse. So cos theta is x by r, and sin theta is y by r. So sorry, I forgot to mention r here. So I'll just write it out. So now what we'll do is we'll substitute x by r and y by r in the equation, and r into x by r plus I y by r. So in this case, let's take r common. Let's take r out of this brackets, and we'll get r by r, and we'll get, essentially we'll get x plus iy, and this r and r can be cancelled out, and initially this is same as the one we saw in the Cartesian form, x plus iy. So that's how we can signify x plus iy in the form of polar form, which is r into cos theta plus I sin theta. Let's do some examples on cmath module. Now let's start off with the cmath modules. First, let's import the cmath module, and we know that a complex number is represented in the form of x plus iy, where x is the real part and iy is the imaginary part. So let us take an example saying that our complex number is 5 plus 2y. Here you can see in this case it's going to pop out a syntax error showing invalid syntax, so we can't represent it in this form. So let us try and assign two variables to represent the real part and the complex part. So we'll have x is equal to 5 as the real part, y is equal to 2 is the imaginary part. So let's say z is equal to complex, and the both, let us input both our arguments here, x comma y, and let's print z dot real, which prints out the real part of the complex number. Here in this case, x comma y is represented in the form of x plus iy. So here the real part is 5, so it prints out 5. So next we are gonna see how we are gonna print out the imaginary part. So print z dot imaginary. So here you can see that it prints out 2. So in our case it is 2 is the imaginary part, so it prints out 2. So now let us see how we find the modulus of z or r in polar form, which is the distance from the origin to the point which we wanted to indicate. So here r is nothing but cmath dot, we use the square root method in order to find the square root of the given function. We know that r is traditionally, when we calculate, it is nothing but square root of x square plus y square. So in this form, when you try to use the cmath module, we tend to use the dot square root method to represent the square root format. So here when we try to calculate square root of x square plus y square, we get r to be 5.385164. So we have already found out r, which is a part of the polar form. Next we'll find theta, which is nothing but the argument. So let's say we'll use dot phase method here in order to find out the argument or the phase angle. So let us say argument is equal to cmath dot phase of z, which prints out the phase angle of the complex number 5 plus 2y. Here in this case you can see that it prints out 0.33805 as our argument or phase angle. So we have got both the attributes of the polar form, which is r and theta. So how can we do it directly? We can also do it directly by using the dot polar method. which directly converts the Cartesian format into a polar form. So we just convert the x and y, which is in Cartesian format, into r and theta in polar form. So here you can see that we have used the method dot polar to convert it directly from Cartesian to polar form, and it prints out the same results as we do it earlier. We found out r and theta individually. So next, we'll see how do we convert a polar form into Cartesian form again. So Cartesian form, so we'll use a method known as dot rect, which is nothing but a rectangular coordinate. Cartesian form and rectangular coordinates are equally the same. So we use dot rect, and it needs dot rect method needs two arguments to be present inside the brackets. So in order to do that, let us first take out a real part, which is or the r, and let's print it out inside this. Let us take 5.385, and let us take the argument or theta and put it inside our bracket. And let when we print rect, we can see that we are getting 5 plus 1.999. So 1.99 is almost close to 2, so we can consider that. So we got the similar answer of what we have earlier taken, which is 5 plus 2y. So here we can consider 1.99, which is almost equal to 2. So next, let us try and see what are the constants or the cmath constants which are present in the cmath module. So we can also try other methods such as dot cos to find the cosine of a given complex number. So by printing cosine, we can see that it prints out the cosine of the given complex number. Here in this case is 1.067 plus 3.4778. So next we can also find the sine, which is sigma dot sine. You can also try tangent, which is sigma dot tan of z. So it prints out the tangent form of the complex number z. So we can also use hyperbolic forms of the given sine, cos, and tan. So we'll say hyperbolic sine, which is sigma dot sine h of z. So it prints out the hyperbolic form, hyperbolic sine of the given complex number z. So we can also find the hyperbolic cos, which is sigma dot cos h of the complex number z, and let's print it out. Similarly, we can also find the hyperbolic tangent of the given complex number z. So now let's see the constants which are present in our C math module. So the first constant we're going to take is cmat dot e, which gives you the Euler's number and prints out the Euler's number, so which is 2.718. Next we have cmat dot pi, prints out 3.1415965. Next we can also print out dot tau, which prints out the tau value, which is 6.283185. There are also other methods which are part of the cmath module, such as dot is finite, is to check whether there are integers or numbers inside our given complex number. So here in this case we have integers in our complex number, so it prints out true. So we have cmath.isNaN method. .isNaN method is to check whether there's an non-integer, there's no numbers in the given complex number, but we do have integers in our given complex number, so it prints out false. So we can also find the arc cosine, arc sine in cmath module. So in order to find the arc cosine of a particular number, we can use dot a cos method to find the arc cosine of a given complex number. So here we found that for our complex number, arc cosine is 0.38 minus 2.370j. You can also find arc sine, which is cmath dot a sine of z, which we are getting it as 1.184 plus 2.37j. And you can also find for arctan, which is dot a tan of z, so let us have a constant c and let us find the base log base 10 log of a given complex number. So our complex, let's find the base 10 logarithm of our complex number z. So here we found it to be 0.731198 plus 0.16525.